All right, good morning or good afternoon or good evening. I really have no idea what time it actually is now, but thanks to the organizers for putting together this really nice workshop. I'm very excited to be here. I'm going to talk about a program I've been leading with HST to obtain UV spectroscopy of tidal disruption events. We've had some really nice introductions, even though I've only been here for the last couple of talks to sort of motivate this work. Yair showed this plot earlier showing that there's this continuum of hydrogen to helium ratios in the optical spectra of TDEs. There are a variety of different possible explanations for why that might be. You heard from Suvi that maybe this is telling us something about the star that's being disrupted, that it's just a helium core lacking some kind of hydrogen envelope. And she also alluded to Nathan's paper here and also some work that James has done saying that maybe what's going on is we're actually observing photoionization effects in some kind of larger reprocessing layer, and that can actually mask and give you, depending on where this reprocessing layer is happening, you can get actually quite large ratios of helium to hydrogen here. These are for 3 different radii for this. So Nathan's going to talk about that much more in depth and intelligently than I can, I think, either tomorrow or the next day. So why would you want to actually get UV spectra of these things? I'm a very simple-minded guy. I like to go where the flux is. This is the composite spectrum of a quasar from about 1,000 quasars from SDSS. You can see the spectral energy distribution in the optical is relatively flat. It turns over about 4,000 or 5,000 angstroms, and most of the flux is coming out here in the UV. So I like to look where the signal to noise is. You can also see that there are a bunch of features. If you're looking in the optical, you're pretty limited to the Balmer series, maybe some forbidden narrow oxygen lines, and of course these helium-2 lines that we've seen. But there are many magnesium-2 for semi-forbidden carbon-3, carbon-4, Lyman-alpha, neon-5. There are lots more atomic features if you go look in the ultraviolet. And in fact, there is some evidence in at least one TDE that maybe there's some interesting behavior going on here. This is PS111AF from a paper by Ryan Chornock, where you see in this spectrum at 24 days, there's this quite broad feature that is not there at 5 days, and it's clearly not there in the host spectrum taken a few hundred days afterwards. There's this transient broad feature, conceivably where you might expect to see magnesium-2 in the spectrum. It's blue shifted maybe by, I think, about 5,000 kilometers a second, so it's not exactly at 2,800 angstroms. But if you've ever done sort of quasar business, temperature, density, velocity diagnostics, looking in the UV is a very natural place. And of course, when we project forward down the road, when we think about the TDEs that LSST is going to be discovering, because it's so sensitive, it's going to be finding these at much larger redshifts than things like Assassin. So if we want to look in the sort of observed optical bandpass for LSST, it's actually going to be rest frame ultraviolet emission. So we really want to understand what's going on in the rest frame UV. So far we've triggered this on 3 sources. We heard about 2 of these from Thomas's talk, Assassin 14Li, which is at a distance of 90 megaparsecs, Assassin 15OI, redshift of about 0.048 or 0.049. And I'll talk very briefly about IPTF 15AF, slightly larger redshift than this. For these purposes, you can essentially treat it as a clone of Pan-STARRS 1 10JH, but with a slightly hotter black body temperature. And we're getting, STIS spectra from, let's say, 1150 to 3200 angstroms or so in the observer frame. Okay, what do these spectra look like? I should say this is all a work in progress. So I'm going to be kind of going through this on the fly. Here is our spectrum of Assassin 14Li. So again, to give you sort of the main numbers, distance of about 90 parsecs, peak luminosity a bit shy of 10 to the 44 ergs per second. Radiated energy, I thought it was about 7 by 10 to the 51. Thomas, you can correct me if that's wrong. Okay, so this is integrated radiative energy, and the SED is actually quite strange. You see this double black body with an optical best fit temperature of about 35,000, and then additional component in the X-rays where it's shining at 10 to the 5th. Okay, so let me give you some guidance to sort of walk you through what you see here in case you don't think about UV spectra a tremendous amount. This is the same plot that I showed earlier, composite quasar spectrum from SDSS, magnesium-2, semi-forbidden carbon-3, going up to carbon-4, silicon-4, and Lyman alpha, neon-5 up there. Okay, a couple things are immediately apparent if you just look at this very briefly. First of all, there's essentially nothing going on in the near ultraviolet, right? Just continuum. All of the stuff that we see sort of going on here at what we'll call far ultraviolet wavelengths. Also, you can see that this thing is quite hot. So this was taken a couple months after discovery by Assassin. This is the same composite spectrum that I showed you before, where it was sort of zooming up in the blue. And this guy is even hotter than a sort of typical quasar spectrum down at these sort of 1500 angstrom wavelengths. So let's zoom in on a couple features of interest here. This is the magnesium-2, which I'm going to take as representative as sort of low ionization lines. Magnesium-2, carbon-3, silicon-2, carbon-2, these kind of features. Assassin 14Li in black, quasar shown in blue here. You see this nice sort of emission feature in the quasar. There's nothing like that in Assassin 14Li. You see this sort of absorption right here at minus 6,000. This is just absorption from magnesium-2 in the Milky Way. It's essentially redshift of 0. There's no absorption or emission from any low ionization features in Assassin 14Li. And that will actually be a trend as we see that in some of the other objects. Yes?
You're only showing velocities here to 10,000, it looks like. Wasn't 11 AF at like 15,000?
Yes.
So there's no absorption even at very high velocity.
So you can walk this out. This plot before was showing sort of from here to here. You can walk it out all the way down to, as high as you want to go. Strictly, smooth continuum, redward of 2,000 angstroms. Okay, high velocity lines. A lot more sort of interesting stuff going on here. So this is zooming in on what I think is helium-2. It's pretty likely, I'd say, identification because we see this in the optical spectrum. Carbon-4, nice strong line that we see in lots of quasars. This, I honestly don't know what this feature is. There's something very weak in quasar spectrum corresponding to semi-forbidden nitrogen-4. And we see in this very strong nitrogen-5 as well. So I think that's a plausible identification, but honestly, I don't know for sure. So you can see broad emission lines, full width, half maximum, maybe like 5,000 kilometers a second. Pretty good speeds. Also, strong, relatively narrow absorption lines. So this is carbon-4 from the Milky Way. This is carbon-4 at the in the host galaxy. If you remember from the previous spectrum, the magnesium-2 was comparable strength to the carbon-4 in the Milky Way. No magnesium-2, but very strong carbon-4 in the host galaxy. And in fact, if you look at, we have pretty accurate 0-point redshifts for this carbon-4. And if you look, it's hard to see at this stretch, but this line right here is actually blue shifted by a velocity of about 80 to 100 kilometers a second. Okay? And that might make you think of something interesting because, in fact, something very similar was seen in the X-ray spectrum for this source. So these are high-resolution X-ray spectra taken by XMM on the left and Chandra high-resolution gratings on the right, slightly lower signal-to-noise. You can see that there are absorption features from very highly ionized material. This is oxygen 7 or 8, 6 or 7 on the left. Argon 14, argon 13. This is really, hot stuff in order to get this kind of ionized material. And these lines are blue shifted again by speeds of somewhere between 100 to 300 kilometers a second. And in fact, that blue shift sort of changes as a function of time. So the optical and the X-ray are both telling us that there's some kind of low velocity outflow, material circularizing around. I mean, it can't be a true outflow because these speeds are not nearly high enough to escape the potential well of this black hole at any reasonable distance away from where they might be occurring. But there's some kind of stuff moving away, these sort of low speeds that are probed by the X-rays and by the rest frame UV lines. Okay, next, IPTF 15AF. So I mentioned that, for these purposes, we're going to consider this more or less a clone of PS1 10JH. This is a spectrum around maximum light, rest wavelength. You see from 15 PTF, 15AF, which is different from PS1 11AF, which is extremely confusing and also very unlikely statistically, but such is life. You can see this broad helium-2 feature that we use to classify these things now, whereas really nothing convincing going on here at H alpha. The only real difference in their evolution is that the black body temperature of PTF 15AF is quite hot at early times. Here's what the spectra look like. I still am trying to wrap my head around what's going on here. Again, sort of nothing going on at this sort of low ionization lines. No magnesium-2, no carbon-3, nothing like that. However, now you see, instead of just emission features, you see these sort of broad lines down here at the blue end of the spectrum. This is plausible. This is some kind of carbon-4. This corresponds to where we see carbon-4. This is where Lyman alpha is in the rest frame, silicon-4. They look sort of Peace Cygni-like. I don't know. Depends on exactly what you assume for what the continuum looks like. They're somewhat blue shifted relative to where the peak of the emission or the sort of 0 point should be for this galaxy. And they're quite broad. Velocities are 7,000, 8,000 kilometers a second. So again, there's evidence in this case for even higher velocity outflows, but only from this really highly ionized material. You really do need these really hot temperatures to get you looking at this. Okay, last, Assassin 15OI. Shown here in black, can sort of, this is just due to the air glow lines. You can ignore this absorption feature. Repeating broken record here, nothing going on in the near UV. In the far UV, plausibly carbon-4, hard to make a strong identification. Plausibly Lyman alpha. Again, you see something that looks, particularly if you look at this as some kind of continuum level, P Cygni-ish like. I wouldn't bet my life on that. But these are very broad features in sort of the high ionization lines and nothing going on in the low ionization lines. Okay, so let me try to summarize what we're learning from these things. And we're sort of going through now and trying to do the actual detailed cloudy-like modeling. It's not sort of the ideal approach because these things are perhaps not as static as cloudy might assume. But we can say, all right, strong blue continuum all the way out to Lyman alpha, bluer than seen in sort of this canonical quasar spectrum, lack of low ionization lines in emission and absorption. Nothing that we can see points to the fact that there's Mg2 in any of these spectra. It is completely unlike normal sight lines to quasars. Lots of stuff going on, high ionization features, carbon-4, silicon-4, definitely an emission, possibly an absorption. See this sort of narrow blue shifted absorption from Assassin 14Li. It's very consistent with what we see in the X-rays. Possible P Cygni lines, again, pointing to some kind of outflow stuff. And there's possible detection of Lyman alpha emission in two of these sources that don't show H alpha emission. Okay? This could be some way to distinguish, I guess that one's out again. Okay. This could be one way to distinguish this sort of, helium core versus hydrogen envelope thing is looking for Lyman alpha. Unfortunately, there are lots of other features going on sort of at those kind of wavelengths. So my take-home message, there are extremely complex photoionization conditions going on in these sources. They're entirely unlike what we see in quasars and really are going to require sort of detailed photoionization modeling if we want to understand the sort of basic physics, the temperature, the density of this material, the distance from the emitting source. Okay? How much time do I have left? Great. As a NASA employee, whenever you give a talk, you are required to pitch a future mission, sort of part of your job. So, if we want to find more of these things, obviously the Assassin survey is doing a great job of finding bright nearby sources. But coming back to this question of, where's the bulk of the emission coming out, looking in the UV is a very natural place to do that. So I've been putting together a project to try to do this, a wide field UV transient survey from a CubeSat platform. If you haven't heard of a CubeSat before, CubeSat is a type of miniaturized space satellite for space research, has a volume of 10 centimeters on a side, and a mass, very strong mass and power requirements. The reason why this is an attractive option is because by fixing the form factor, commercial companies will make sort of standard spacecraft parts like communication, power, computing, all the sort of normal things that you need to operate any spacecraft, and you can buy them for relatively cheaply, and because they're relatively compact and standardized, you can fly them as sort of, if there's extra space in other bigger missions that are going up there. So this is just to show you how most of them are currently being deployed right now. Since most of the cargo that's going up to space is going to the International Space Station, they have these sort of robotic arms that kind of push these things out of the ISS. And this is actually the first 2 satellites from Planet Labs, if you've ever heard of them. They're doing, they have a large number of wide field optical imagers, but they're pointing down at Earth to do Earth imaging instead of pointing up at space for commercial purposes. So they're a big startup in San Francisco that's gotten a lot of, like $300 million actually, to do this kind of stuff. So the satellite that I've been working on called CUTI, the CubeSat Ultraviolet Transient Imaging Experiment. Science, as you can imagine, UV transients and variables. Because of the space constraints, you're quite limited in how large your telescope can be. We have a design with 8 centimeter refractive optics that at an f2 ratio gives you a field of view of about 121 degrees squared. Just for comparison, what this looks like, this is the field of view of Galax, this is the field of view of the Swift view of VOT. This really would be kind of the first time of doing wide field imaging in the ultraviolet. It's a 6U spacecraft, so actually 6 of those, 1U units in a low Earth orbit. And the nominal survey strategy would be to survey, let's say, 1,700 degrees squared every 95-minute orbit or so. So how do we actually get this working? It's like a Petzval lens-like system. I think there are 7 or 8 optics in there that give you the field of view and pretty good imaging. You can get now commercially available E2V CCDs with good QEs if you're looking in sort of the near UV, let's say wavelengths 250 to 300 nanometers. Very efficient filters at these wavelengths. We heard from Thomas, he was saying our pixels are, 1 minute, excellent. Big, the pixels here would be even bigger. But because of the high throughput, you can actually get comparable effective area to the Swift UVOT, even in this little package. So very briefly, science yield from this supernova shock breakout, TDEs. You can imagine, depending on what your belief about the rates are, somewhere between a few and a few tens per month with that kind of survey. So that's it. I'll finish there. Take any questions. Yes. you could certainly imagine with a successful one going in for future proposals and saying, we want to build a fleet of these things to do the entire sky. You know, you don't know exactly what the cost decrease is, but you could fit that in, let's say, a mission of opportunity type program, $60 million to build, I don't know, 30 or 40 of these things to do a significant chunk of the sky at any given time. And people are spending a lot of time thinking about crazy things for CubeSats like formation flying and all that. You don't really need to do that. You just need to get them up there, not in the exact same time.
Question? Was there a question there?
Yeah, oh yeah. So, yeah, I was wondering what is PPF, 15AF, came out a little bit out of the blue, or there's nothing PPF. And also, can you confirm what Ryan Jornock was seeing to be magnesium or hydrogen or helium absorption lines?
There are no magnesium, hydrogen or helium absorption
Yeah,
lines.
so I mean, his was a higher redshift, so is that those absorption features consistent with what you were seeing
We
with HST?
We don't see any magnesium-2 absorption features in any of the three sources that we looked at. Now, the thing about the Pan-STARRS 1 11F paper is that this feature was transient in nature, right? They detected it once at 24 days after maximum light, and then they looked again and it wasn't there.
Right.
We just have single snapshots for all of these. So it's conceivable that that's going on, but in none of...
Or later than...
Yes,
yeah.
that's right. By, let's say 2 months after.